Do we set it equal, just set it equal to 0 again?
No. To figure out what the domain is, we really need to figure out what x cannot be. The trick to domain is always to figure out what x can't be. Is there anything x can't be in this function? Is there anything that creates problems?
A negative, maybe?
No. If I made x minus 10, it's still, I can figure out what f of x is. In other words, there's no value of x that causes me to divide by 0, that causes me to have to take the square root of a negative number, or any of the things that I cannot do. And that's really what we're looking at for domain, is you can't divide by 0, you can't take the square root of a negative number, and you can't take the log of a negative number or 0. And there's not many other domain restrictions. That's pretty much it. So when we look at a quadratic like this,
Oh wait, it's 3x cubed, not squared.
Okay. Doesn't matter for domain.
No.
For domain, there are no problems created by plugging in any number you can think of for x. So the domain is all reals.
Oh, okay.
Okay. And let me see if I can read the next one. It's the square root of x squared minus 1.
Yes.
Okay, so how are we going to figure out the domain on this one?
Is it greater than equal to that?
So you take whatever's inside the radical, fine, and you say it has to be greater than or equal to 0.
Yeah.
Because we can't take the square root of a negative number. We can take the square root of 0. So now let's solve this inequality here. So what's the next step in solving that inequality?
Do you add 1 to either side?
Now, this might not be totally obvious, but what this means is that x has to be greater than or equal to 1, less than or equal to negative 1. Notice that if x was minus 2, this, what I have circled here, would be true. Because we would square it, it would be 4, and 4 is greater than or equal to 1. So our domain, let's put it in interval notation.
Yeah.
Starting from the left side of the number line.
So is it negative infinity, comma, negative 1?
Can it be equal to 1?
Yes.
So do I need a parentheses or a bracket here?
A bracket.
And then in combination with parentheses or bracket here?
Isn't it bracket?
Uh-huh.
Is it bracket 1, negative 1? Or negative 1, 1?
It's 1 positive infinity. In other words, on the number line, this is 0, and this is minus 1, and this is plus 1. X can be anywhere in this region. The only thing it cannot be is in between minus 1 and 1. Because if it is, we end up with a negative number inside the radical. So this is correct, and you always put parentheses next to infinity.
Okay.
Okay. Let's see if my phone will show me the next one. My phone goes into sleep mode. so it always goes dark. Okay, here we go. The last one here looks like x minus 5 divided by square root of 2x plus 1. And again, this is f of x. Okay, so the domain on this one needs to be, how am I going to figure that out?
Greater than equal to 0.
Well, normally, what is greater than or equal to 0?
The 2x plus 1.
Okay, so normally I would say 2x plus 1 has to be greater than or equal to 0. But notice that because this is the denominator, it can't be equal to 0.
Oh, okay.
If it was in a numerator, I could make this statement. But since it is both under the radical sign and it's the denominator, it has to be greater than 0. It can't be equal to 0.
Okay.
So now let's solve this inequality. What do you get when you solve this?
So you have to subtract 1.
Okay, so 2x is greater than negative 1.
And then divide by 2.
So x is greater than negative 1/2. So now let's write that in interval notation.
So parenthesis negative 1/2 and then infinity.
Comma.
Yeah, comma.
Correct.
Okay.
And it's parentheses because it's greater than. And notice that this x in the numerator didn't really affect us at all. There's really very few restrictions on domain. I think I named all of them, and that is you can't divide by 0, you can't take the square root of a negative number, and you can't take the logarithms. You have to take logarithms only of positive numbers.
Yeah.
I don't know of any other restrictions, but okay, let's have a look here. What's next? All right, let's see. Determine if the function is continuous. If it is not, tell where the discontinuities occur. First one is the same one we were trying to determine the domain of.
Yeah, they're all the same problems. It just asks.
Okay, good. All right, so let's again, we made this look like that with the restrictions that x cannot be equal to plus or minus 3. Okay, so if we graph that, this is a hyperbolic function. If we look just at that, where's our vertical asymptote going to be?
At negative 3.
Okay. So we have you've had vertical asymptotes, right? And horizontal asymptotes? Okay. So where's the horizontal asymptote going to be?
Is it 1?
It's 0. If your denominator is a higher power variable than your numerator, it's always 0.
Oh, right.
And I could tell that from looking at this. This was an x in the numerator and an x squared in the denominator. So I know how to graph this. It's going to graph something like this. Like most hyperbolic functions, it looks a lot like that. There is one further restriction that since x cannot be equal to plus 3, I have to put a hole in the graph right there. Okay, so there's my graph. So now let's figure out what the domain is. Oh, no, we didn't have to figure that out. We already figured that out. We have to figure out whether it's continuous and where.
Or if it's And if it's not, tell where the discontinuity is.
Yeah, here, let me read the determine if it's continuous. If not, okay. So is this continuous?
No.
What's the working layman's definition for continuity?
Isn't it like if you can pick up your pencil, or
Yes.
that's how
Yeah.
yeah.
I can't draw this curve without picking up my pencil. Where do I
Right.
have to pick up my pencil? I have to do it in two spots.
At -3 and 3.
Right.
Okay.
And that's it. Okay, let's see here. Let me look at the next one. 3x cubed minus 7x plus 1. Now, there's not a whole lot of things that'll make stuff discontinuous.
Mm-hmm.
You need a vertical asymptote, you need a hole, or a radical sign. In other words, for the same reason that the domain is all real numbers, this has to be continuous from negative
Right.
infinity to positive infinity. It's a cubic, so it's not a parabola, but a parabola would also be continuous throughout the domain. You talk about continuity throughout the domain, and the domain of this thing is minus infinity to plus infinity, and even though a cubic function usually looks something more like this, same general principle. The domain, it's continuous the whole way. There's no place I have to pick up my pencil.
Okay.
Okay, the third one was square root of x squared minus 1.
Mm-hmm.
If I graph this, let's see, that's the whole function, right? Yeah. Where's my vertical asymptotes? No, let's see, what did we figure out for the domain? The domain, x has to be less than 1 or greater than 1.
Right.
And this is not defined between -1 and 1.
Mm-hmm.
To the right of 1 looks something like that.
Mm-hmm. So it's not continuous?
To the left of 1 looks something like that. It's defined at -1 and it's defined at 1.
Mm-hmm.
So let's assume, I'm not positive that the graph looks like that, but I know it looks something like that in the middle.
Uh-huh.
There's no part of the domain. You can't have an x value that is between -1 and 1. So this would not be continuous, and it would not be continuous from -1 to 1. I can leave my pencil, whatever this thing looks like to the left of -1, it's continuous left of -1. And it's continuous to the right of 1.
Mm-hmm.
Let's see, when x is 1, it's 0. When x is 2, we're taking the square root of 3. When x is 4, taking the square root of 15. So it does look something like this. Okay?
Okay.
And the last one was where we were dividing by, look again. My phone's doing screwy things.
Oh, it's x minus 5 over the square root of 2x plus 1.
Okay. Now, right offhand, I don't know how to graph that. I could put it into my graphing calculator and look at it, but let's try to figure out continuity based on the domain that we came up with. The domain we came up with was x had to be greater than negative 1/2, right?
Mm-hmm.
Because when x is negative 1/2, we have 0. We'd be dividing by 0. So this is clear, which means that when I graph it, I can only start at negative 1/2. And x can be anything after that, so it might do something like that, but it's going to be continuous regardless.
Right.
And it's an open circle right there. And I didn't mean to draw it as a closed circle because it cannot be equal to negative 1/2.
Right.
But no other problems happen after that. It may not look precisely like that, but I know I'm going to be able to leave my pen on the paper. All right. Look what's next here. Determine the intervals in which the function is increasing or decreasing. Oh, I love it. I'm getting into calculus already.
Fun.
Let's see, that was x minus 3 over x squared minus 9, which was equal to 1 over x plus 3, which is the hyperbolic function, and there's a vertical asymptote at minus 3, so we figured it looked like this, and there's a hole right there. So where is this function increasing?
On, is it the negative, like negative 3?
It's nowhere.
Nowhere?
Nowhere in the domain is the function ever rising. What increasing means is that as you move to the right, you go up in the y-axis. In other words, this function is always increasing. As I move to the right, I'm going up vertically. Whereas in this function that we just drew on the left, starting from here, as I move to the right, I'm always going down. And then I go across the vertical asymptote, and I get up to here, I'm always going down forever, all the way out to infinity. So it's never increasing. And what the rest of that thing say? The instructions. What intervals is it decreasing? They want the intervals increasing and the intervals decreasing. Let's put it in interval notation. In fact, I'm going to need more room than that. We got 1 over x plus 3, and x can't be equal to plus or minus 3. So, what intervals is this decreasing? What's the first one?
Is it like negative infinity, comma, negative 3?
Okay. Where else?
And then 3, comma, infinity?
This is negative 3 still.
Oh, and then positive.
Actually, you got to account for that hole. Remember, there's a hole at 3. So we got to go up to 3.
Okay.
Can't be equal to 3. And then we got to combine that with one more interval. So there's 3 intervals that have to be talked about for this is where it's decreasing. Now, have they talked to you anything about calculus, about first derivatives or anything? Okay. One of the things about calculus is that The first derivative will always be positive when the function is increasing, and it will always be negative when the function is decreasing.
Oh, okay.
So I wouldn't think they would have talked to you about that yet, but talking about increasing and decreasing functions is the first steps of calculus. Okay, the second function. Let me graph this on my Wolfram alpha, because we do need to look at this. I'm curious they ask you this second question because, what is that function again on the second one? It's 3x cubed.
Cubed minus 7x plus 1.
Do you know this Wolfram alpha at all? It's great for if you're not on your calculator and you're on your computer. It's a better calculator than your calculator is. Okay. Notice that it shows me the graph in two different scales, and it also does some nice things like show me the roots. I don't have to go in and put trace to find out the 3 places that it crosses the x-axis. It shows me all 3 of them right here. And it'll give you solutions, and it gives you the domain. Notice it gives you the domain is all real. So this is well worth knowing about. It's called Wolfram Alpha.
Yeah, I read it.
.com. And we want to know where it's increasing and where it's decreasing. How in the world? They must expect you to do this problem on your calculator.
Yeah, I think they do.
And what would we do? We would look for a local maximum. We would try to figure out what the x value is there, and it looks like it's -1. And it's increasing from -infinity to this x value. It is then decreasing from that value to that value. And that is not +1. It's close to 1. But you'd have to figure that out from your calculator. One thing this will not do is let me know that number. And then it's increasing again from this point all the way to there. Do you know how to do this on your calculator?
I'm trying to figure it out right now. I'm not very good with the calculator.
Okay, here, my calculator's not working, but I remember how to do it. Do you have a TI-84?
Yes.
Go ahead and put this in as y equals this function.
Yeah, I have it as in, I already have it in and then I graphed it.
Okay.
And it looks like that on the...
Okay, now pull up math.
Okay.
And what are your options when you hit the math key? What does it give you? You can look for maximum or minimums.
Yeah, it says F-min and F-max.
Try to find this maximum right there. And the way you got to do it is, first of all, go ahead and click on maximum.
Okay.
And now you'll have to trace and click to the left of that and to the right of it. And it'll tell you what the maximum is. And it should tell you x equals -1. I'm pretty sure what that is at -1. I was bragging on Wolfram Alpha and it can't do this. And actually it might be able to. I'm not sure I know how to do it on Wolfram Alpha. In other words, once you've told the calculator you want to find the maximum, it's going to ask you to click on 2 points and it'll find you the maximum between those 2 points. So if you put your
Right.
calculator on trace and click to the left and to the right, it should find this value right here. It should tell you x is -1 and maybe even y is 5.
Okay.
And incidentally, if you ever have questions about how to use your calculator, there are some great YouTube videos. If you
Okay.
just go into YouTube and say TI-84 maximums, it'll show you a little 5-minute YouTube clip on how to find the maximums of a function.
Okay.
Okay, but so let's not spend the rest of our time trying to do that. What your calculator is going to give you is the x value where that maximum occurs.
Okay.
And then if you look for minimums and you go over to this point and you click to the left and you click to the right, it'll give you the x value where this local minimum occurs. Okay? For the sake of argument, let's pretend that it is at this point is where x equals -1 is where that little local maximum occurs. And the local minimum occurs at, it looks like, let's call that 0.8. It's not 1. Okay, so now let's say, what intervals is this function increasing? Negative infinity to what?
To 1, -1.
-1. And we're going to use a parentheses there because it's not increasing at -1. It's 0. That slope has changed to 0 at -1. However, it's increasing again from where?
0.8 to infinity.
Right. So that's the levels that it's increasing on. How about decreasing?
Is it like
-1 to, in other words, it's from here to here. That's the only place this function goes down as you go to the right.
okay? So negative.
So there's the answer to this problem. It's increasing
Okay.
on this interval, it's decreasing on this interval.
Okay.
Okay. The next function, square root of x squared minus 1. Let's graph that just so we know what it looks like. So that is x squared minus 1 quantity raised to the 0.5. The other nice thing about Wolfram Alpha is you type in exactly this is what you typed in. And notice your calculator doesn't do that, and it's very hard to get it typed in properly sometimes on the calculator. In other words, it's a question about where you put your parentheses and everything else. So having this feedback like this is very helpful. It tells me that I typed it in properly. Okay, and if we look at that, that's kind of how I drew it when we were graphing it. And Wolfram Alpha, the orange line represents the imaginary solution. The blue is the real solution.
Okay.
Okay? So for your class here, we wouldn't have the orange. If you did this on your calculator, you're not going to see the orange. You're going to just see these blue lines. Okay, where's this decreasing?
Um, is it like -1?
Okay? It's important to realize how far to the left that goes. When we did domain, what was our domain?
Negative infinity to comma 1,
Okay.
and then -1, comma infinity.
So, in other words, if we carry this out, it goes all the way up forever. So this thing is, let's do decreasing first. Decreasing on the interval negative infinity to what?
Positive or regular? Just infinity?
Just from there to there.
-1. Oh, okay.
To negative 1. From negative infinity to negative 1, it's decreasing. Where is it increasing?
1 to infinity?
Yes. Okay. And the last one was, what is it again?
X minus 5 over the square root of 2x plus 1.
X minus 5 divided by the 2x minus 1 raised to the
plus 1.
2x plus 1?
Yeah.
Quantity raised to the 0.5 power. So that looks correct. Oh, no, it was, notice that it didn't, I didn't type it in right. It's not going to affect things, but I need a parentheses around that x minus 5.
Right.
That's the beauty, is in your calculator it wouldn't tell you that you've made a mistake, whereas this tells you right away. Okay, so notice that when we did the domain on this, our domain was x had to be greater than minus 1/2. Well, if we look at this graph, there minus 1/2 would represent a vertical asymptote, and this graph is approaching that vertical asymptote as we go towards 1/2 from the right. So this is increasing on what interval? It's not decreasing on any interval. If you look at it, it's always increasing.
Is it how do you know exactly what number it is, though?
It's
Like
we figured out the domain, and the domain was x has to be greater than negative 1/2. So you can't even put in a value of x less than negative 1/2. So it's increasing on the interval negative 1/2 to infinity. In other words, if I go all the way over to here, I'm at negative 1/2, and then no matter how far I go to the right, it's always going up. And that's what increasing means.
Okay.
In other words, if I take a graph, just a normal looking graph, and I do something like this, well, that's increasing from negative infinity to this point right there on the x-axis. It's decreasing from this point to this point on the x-axis, and then it's increasing again from this point to positive infinity. That's what increasing and decreasing means. All right, let's see what else we got here. Okay, the next one says, determine whether each function is bounded above, below, If it's bounded above, bounded below, bounded or unbounded. Bounded has to do with the y values. As an example, if I look at the sine curve, I know you haven't had trigonometry yet, but if you probably know the sine curve. Looks like that from negative infinity to positive infinity. That's bounded above by 1 and below by negative 1. In other words, I can draw a horizontal line. That's the upper bound. It never gets above 1. And it never gets below minus 1. So the sine function would be bounded above by 1 and below by minus 1.
Okay.
If I looked at a function like y equal x squared, is that bounded?
Is it bounded below?
It's bounded below by the line y equals 0. It's not bounded above. Y can get as big as it wants. If you put in a big enough value of x, y will get to infinity. But there's no value of x where y will be less than 0. So it's bounded below. Okay, so that's what they're talking about when they're talking about boundedness. Okay, well, I remember how to draw that first function. There's a vertical asymptote there. And there's a hole right there. So the question was, is it bounded above?
Yeah. Or is it bounded above and bounded below?
It's not bounded above because this thing goes to infinity. It goes up all the way. In other words, just because I've stopped drawing it doesn't mean it stops.
Right.
If you look at the graph of this, it goes all the way up to infinity. So it's not bounded above.
Okay.
It's not bounded below because it goes all the way down to negative infinity. Remember, when we're talking bounded, we're talking about what the y values do.
Yeah.
Now, the consequences of that hole is where x equals 3, and the function becomes 1 over x plus 3. So that hole is a value of 1/6 on the y-axis. So whether that represents a bound above or below, I don't think so. That's in between. Also, there's a horizontal asymptote at y equals 0, and the function does not ever cross that. So y can never be 0, and that's the only thing y can't be, is 0. Have you dealt with range yet?
Yeah.
Okay. When we were looking at this function, the only thing we talked about was domain.
Yeah.
But if we talk about range, that is whatever y can be. And y can be any value except, can't be 0, and it also can't be 1/6, because x can never be 3. X was locked out of being equal to 3 by the original function. So since x can never be 3, there's no way for the y to ever attain the value 1/6. It doesn't do it below the x-axis, and it never hits it above the x-axis because of that hole. But I don't think that affects the boundedness of it. All right. The second function looked like it was just a standard cubic function. It had a hump in it. it looked like this. That bounded?
No.
Not above or below. This thing will go all the way to negative infinity, and that thing will go all the way to positive infinity on the y-axis and the x-axis. But so that's not bounded at all. The third one was square root of x squared plus 1, which looked like this. Is that bounded?
Is it bounded below?
It is bounded below. By what?
-1 and 1.
That's the x points. When we talk about boundedness, we really are talking about the y values.
Oh.
So the lower bound would be defined as y equals 0.
Okay.
Y can never go below 0 because y is equal to the square root of x squared plus 1. This is always, excuse me, that's always a positive number. Is it x squared plus 1?
-1.
It is -1, yeah, because we did all the other problems based on x squared minus 1.
Yeah.
And that's what caused x to have to be less than 1 or greater than 1. In other words, this point here is -1 and 1, but it's bounded below by the horizontal line y equals 0. And it's not bounded above. Okay, the third graph was f of x equals x plus 5 over the square root of 2x plus 1, something like that?
Yeah, that's right.
And you remember that there is a vertical asymptote. It's always helpful to know where these vertical asymptotes are, because they're the ones that are going to give you your domain, they're going to give you your range, they're going to give you your continuity, they're going to give you the bounds, everything. And I know this is what it looks like, because we looked at it on Wolfram Alpha. It kind of looked like this. I don't know that it necessarily went through the origin. But what this means is that as x approaches -1/2, y does what?
Increases.
No. If we are approaching -1/2 from the right side. In other words, I see why you said increases.
Yeah, so it decreases.
Well, it goes to negative infinity. In other words, we can only approach the number -1/2 from the right side. It doesn't exist to the left of -1/2. But it means that as we get closer and closer to -1/2, y gets closer and closer to negative infinity. Whenever you divide by 0, you're going to be dealing with infinities. So this thing is not bounded from below. It'll go all the way to negative infinity.
Okay.
And it's not bounded above. The y values will go all the way to positive infinity.
Okay.
It's bounded to the left and the right, but that's not what bounded means. Bounded means vertically or horizontally. I mean, up and down. Okay, what's the next thing? Let's see. We got off to a little bit of a late start, so I don't mind going a few more minutes if you need to.
Yeah, that's fine.
Yeah, the last thing on here is determine if the function has extrema. If it does, tell where it is and where it occurs. Be specific. Okay. First function. You know what an extrema means?
No.
It's a local minimum or maximum. And by that I mean, by local, it's any part of the function, if it has a point on it where every point to the left is above and every point to the right is above, then that is a local extrema. That would be a local minimum. If I had this function, this would be a local maximum because the point immediately to the left of that is lower and the point immediately to the right of it is lower. This is a local minimum because points to the left and to the right are higher. Do we have any local minimums or maximums on the graph with the asymptote? That one right
No.
No, there aren't any. There's no place anywhere on here where it's either a maximum or a minimum. So that has none. The second one, when we looked at it on Wolfram Alpha, it looked like that. And when we were trying to find out where it increased from negative infinity to right there. That's a local maximum. It then decreased from that local maximum to a local minimum. On that interval, it decreased. Remember, we pretended that that was 0.8, and that was -1, I believe.
Yeah.
And so there's two extrema on this. One would be at x equal -1, and the other would be at x equal 0.8. And that's the only two local extrema on this curve.
Okay.
So all of these things are related. Local extrema, boundedness, all of that. Okay, the third one was
The square root of x squared minus 1.
that one, right?
Mm-hmm.
Does this have any extrema?
No.
That's right. There's no rounded parts. There's no that or that in the function. Now, let me take that back. There's the other place that you have to consider extrema is the endpoints. This function is square root of x squared minus 1.
Yeah. But it doesn't go up or down from like either of the endpoints, so wouldn't it just be no?
Well, we've got these endpoints right here. We can't consider the endpoints of infinity, but we have a couple of internal endpoints here. And in fact, this represents not only a local minimum, but an absolute minimum. In other words, you have local minimums and then you have absolute minimums. Absolute minimum being for the entire function, that's the lowest value we get, 0.
Yeah.
So when you're looking for extrema, you not only have to look in between at the function, but also at the endpoints or the internal endpoints. So I do believe that this would be an extrema right there and there.
Okay.
That's a minimum. And finally, the last one, how did it graph? X had to be greater than -1/2. So it graphed something like that. And if I put arrows on there, it makes it arrows merely means that it goes on forever down, but never crosses this vertical asymptote. And this arrow means it goes to infinity on the x-axis and also goes to infinity on the y-axis. So do we have any extrema here?
No.
No, we do not on this one.
Okay.
So I'm positive on the first two and the fourth function. The only one I'm not 100% sure of is that third function where I said we did have extrema at these 2 points here. 95% sure of that, but that's all. I guess you'll find out in class.
Yeah, I'll ask her about it.
Okay. All right. So it looks like that's a good place to stop.
Yeah.
Okay.
And just while we're talking, do you know if you have any time open on Monday?
I do. Let me pull it up here. I have to keep these things all closed out when I'm running a GoToMeeting session, otherwise my computer will crash. Let's see, let me go to next week. Okay, that's my Monday. I'm tied. I'm actually in the Highlands Ranch area from 3:30 to 5:30. Well, I have an appointment from 4 to 5 in the Highlands Ranch area.
Okay. I could do 5 to 6 if I could just meet you at Highlands Ranch. Or would you rather?
I can get to Highlands Ranch. I could do 5:30 to 6:30, or I can get home. I can get home by 5:30 and do it online from 5:30 to 6:30. Doesn't make any difference to me. It's completely up to you. The in-person, I do charge a little bit more for that, and I don't know if you consider it of any more value. So
maybe. Do you think could I text you about it? I just am thinking because of my calculator. Because I'm honestly struggling with the calculator thing.
Okay. Okay, let me put you in here. I'm going to put you in from 5:30 to 6:30.
Okay.
And to be determined.
We can either do that.
Yeah, we can either do it at the library or online.
Yeah.
And yes, you're right. The one thing that in person is going to work better on is that calculator. Especially since mine's broken. So,
yeah.
But I do remember how to use it, so I know how to use it. So why don't let me go ahead and put a note here that we'll do it at the library.
Okay.
And then if something comes up where you want to do it in person instead of the library, you can let me know. But as of right now, we'll plan on meeting at the library upstairs at 5:30, excuse me.
Okay, perfect.
Right.
Thank you.
Okay, Morgan. I'll see you Monday.
Okay. Bye.